Good afternoon and welcome to TechXtend Programmer's Paradise webinar with PGI, 5 times in 5 hours, porting seismic CPML using the PGI Accelerator model. Our agenda for today is a brief overview of who we are at TechXtend, then our presentation of 5 times in 5 hours, porting seismic CPML using the PGI Accelerator model, given by Matthew Colgrove of PGI, followed by questions and answers and then a brief summary. Here's a brief slide of who we are here at Programmer's Paradise TechXtend. We are a validated reseller of developer and infrastructure tools. We can be found on the web at www.techextend.com, where you will find a copy of our ALM Worldview ecosystem. Our ALM Worldview ecosystem contains industry-leading tools for your end-to-end development needs to define, design, develop, test, deploy, and manage. And with that, I'm going to turn it over to Matthew for the presentation.
Well, great. Thank you. Hopefully everybody can hear me. But again, I'm Matt Colgrove. I'm with the Portland Group. I'm an application engineer here. So today I'm going to be presenting some of the work that I did on a particular application called seismic CPML, but I'll back up a little bit and give you a brief introduction of the PGI Accelerator model and exactly how it can hopefully be applied to some of the projects you all are working on. So first, I'm going to give my one marketing slide, so I do apologize here. This will be a technical presentation, but I wanted to first introduce who PGI is. Some of you may not be aware of what we do. We are a compiler vendor, and as well as some of the profiling and debugger tools that go along with it. But that's our primary business. We target specifically x86 as well as more recently NVIDIA GPUs. We've been around since 1989, and the compilers themselves are actually preceded us. Primarily, we focus on high-performance computing. Not to say that people outside of that community do not use our products, but that is our main target audience. So we're not in business to compete against the GCCs or the Microsofts of the world. We're specifically trying to provide tools to more the physicists, the engineers, the scientists. And so Fortran is one of our largest customer bases, our Fortran users. So classical compiler optimizations, vectorizing, auto-parallelization, targeting all multiple platforms such as Linux, Mac, as well as Windows, and including a Visual Studio integration. So, but that's about the last 4 or 5 years we've been working closely with NVIDIA to come out with a CUDA product specifically targeting Fortran, and more recently we have a CUDA x86, so we're using CUDA C programming but targeting multi-core. But today's talk, I'm not, just given our time, I'm going to focus strictly on the PGI Accelerator model. And what that is if you're familiar with OpenMP, it's very similar in that for C, you can just simply add in some pragmas. In this case, we see the pragma ACC, or if you're in Fortran, a directive, and you just define a region of code that you say, compiler, take this code and offload it for me to the GPU. So it provides a very quick way for you to gain access to the GPU. Not to say that parallel programming is easy. It is not. In the accelerator model, still, you have challenges to be able to get your code onto the GPU in some cases. Some cases it is easy. But it is intended to make it easier. So some of the advantages is that if you've ever worked with CUDA, you know there's a lot of bookkeeping, a lot of management of your data. You have to write your kernels. You have to be able to optimize your kernels. Well, the compiler can handle a lot of that details for you. So it allows you to focus just on your algorithm, just on the science at hand versus all the extra bookkeeping work that goes along with CUDA. It's easy to get started, so you can work on small portions of your code at a time. So work on this loop here, offload it to the GPU, just small portion of your code, prototyping, so you can use it for different algorithms. Well, which one works better? It's much easier and simpler to get started. Just, well, let's see what happens here, let's see what happens here, versus a CUDA where you may take days to re-implement it. And finally, portability. So for compilers that don't recognize the accelerator model, or even with PGI turning off a flag, the code just becomes straight line C or Fortran. No need, so you can actually just put this directly back into your mainline source tree without worry for pollution or being able to have to have separate branches in trees, one for GPU, one for CPU. You just put it back in your main line, and just with a simple compiler flag, you can turn it on or off. So we have had many success stories. These are some of just a few of the success stories that of various companies and universities that have used the accelerator model and seen great speed up, depending on exactly what they're doing, the type of code, and it'll largely vary on how fast you can achieve and how long it takes. And you can see that we've had a lot of interest in the oil and gas industry, seen lots of success there. One of my personal favorites is the Games UK project. I actually worked with Professor Wilkinson on this. It got to develop a great relationship with him. It was very pleasing to see some of the results that he was able to. And this was a particularly difficult one in that it was Games UK predates F77 or Fortran 77. So it's this F77 very serial code. And he had to do a lot of work to be able to, forget the accelerator model, but just to get it into changing the algorithm so they could be parallel. So a lot of his time was spent not so much using the accelerator model, but just reworking his code to make it parallel, something that some of you may have to do as well, depending on what you're starting with. So a typical experience is that you start adding directives or pragmas in your code, and you may see some slowdown. Don't despair at this point. Usually a little bit more tinkering, a little more adding in different directives, modifying code, you will start to begin to see speed up. Again, the directives make it easier for you to do since you're concentrating on just the algorithm and just sections of your code at a time. So you're able to tune and makes it just a faster development path. So for those of you that are new to GPU, I'm going to give a brief explanation of what an NVIDIA GPU architecture is like. Here we have a Fermi, which is the current generation of NVIDIA GPUs, or at least our representation of it. On the left-hand side, you see the host memory. Much of your computation will be done here. This is traditional. Your serial portion will be done on the CPU. And then you need to actually, because this is a detached device, you need to move your data. Any data that's going to be calculated or used on the GPU needs to be copied over. And oftentimes, this is where your performance bottleneck is, or it's your first performance bottleneck. It's not your only one. So whenever possible, you want to minimize the amount of data that gets copied, and more importantly, how often it gets copied. So you want to minimize the number of times as well. So once in device memory, though, it's still not done. This is a high bandwidth but low latency memory. So in other words, you can get a large throughput on the memory, but it takes quite a while to do that. So whenever possible, you want to use contiguous data. So if your data is contiguous, the more likely it will be able to be held in the higher level caches here. Now, in older generations of NVIDIA GPUs, there was only one level of cache, and it was software managed. Software meaning you, the programmer, had to manage it yourself. Through use of shared arrays, and you still have access to that, and the compiler will actually automatically optimize for shared memory whenever possible. But it just keeps in mind for you the algorithms that you want to, that best are able to best utilize the GPU are those that are data parallel, where you have contiguous data. So what happens is that the data gets brought up into one chunk into these streaming multiprocessors here. That's the group of threads here. Gets brought up into one chunk. And what you have is you have multiple of these multiprocessors, depending on exactly which device you have. That's one of the differences between the different GTX or Tesla or whatever type of a device you have is the number of multiprocessors. Within that multiprocessors, you have 16 thread processors. These thread processors are SIMD, or single instruction multiple data, meaning that each one of these threads processors are executing the same instruction at the same time, just on different data. These are dual pumped, meaning that there's actually 2 threads per processor active at any given moment for a total of 32. And this is a special term called a warp. A warp is the active processors being run on a streaming multiprocessor. So it is very important for this data locality to be able to bring up in chunks, so all your threads can so what happens is if one thread goes to memory, all threads have to go to memory, and if the memory is not contiguous, all the other threads have to wait for the other ones to get its data. If it's in one contiguous chunk, it can be brought in at one single instruction. So how your data is laid out is very important. Now, for CUDA programming, what happens is that the programmer will create what's called a kernel. And you can kind of think of a kernel as a little bit of serial code, where each thread executes the same bit of serial code, just on different data. So they're all executing this at the same time. These threads are organized into a grid. And a grid is kind of, think of your whole problem space. If it's an array, think of multi-dimensional arrays or just a single-dimensional array, that's your grid. And then it's divided up into what are called blocks. And a block gets scheduled on a streaming multiprocessor. Within that block, you actually have then your thread block. So the individual threads within that block. And those get what's executed on it. The good thing about the accelerator models, you don't really have to worry about the details here. Let the compiler figure that stuff out for you. You can override the compiler. You have ways to adjust it if you want to have that control, but you don't need it. So let's go on to look at a simple example of how you can use the accelerator model. Here we have a small Jacobian solver. It's going through multiple iterations. This is C code, so I'm using a pragma here, where we've defined pragma ACC region and give the region of code you want to offload to the GPU. So what happens? So we enter our iteration, our for loop, our first outer for loop. This is on the host. We enter the ACC region. So the first thing the compiler does is it actually allocates memory over in the device. And then it needs to copy its data. In this case, it only needs to copy B, the B array, over to the device, because it's smart enough to look into this and to do its analysis to realize that A is not needed on the right-hand side, so we don't actually have to copy the data. So we only do a copy out on this one. So next, we actually launch the first kernel. The compiler has auto-generated a schedule of how it's actually the blocks and the threads, how it's actually run on the GPU. And it's automatically created the kernel for you. Launches the kernel, does the transformation, launches the second kernel, copy back from A to B. Now we're at the end of the region, so we need to copy our data back. In this case, both A and B need to be copied back. Deallocate the memory on the device. Then we go back over the top. Okay, now we have to do it again for the second iteration. We allocate our data, copy over the new B, launch your kernels, do the transformation, copy it back from A to B, and so forth. Now you should begin to see a problem here. In the previous slide, I said one of the biggest challenges for performance on these is copying data. Well, you want to minimize that. And here, each and every iteration of this iteration loop, we're copying data back and forth, and we're wasting a lot of time. There's absolutely no need to copy this data back and forth between iterations. So instead, what we can do is add what's called a data region. And so this spans across either multiple compute regions, that's the ACC region, and host code. So it essentially gives you finer grain control over when the data is copied. So here we have a copy clause, that's bidirectional. What that means is at the beginning of the data region, you copy B to the device, and at the end of the data region, you copy it back. Local means just allocate data on the device and do no copy. In this case, A is just a temp array used to hold intermediate values of B between iteration to iteration, so there's no reason to copy it back at all. So when we enter the data region, the device arrays are allocated. We copy over B. Again, A is local. No copy is necessary. Now we entered our region. We launch the kernels, do the transformation, copy it back again. Now at the end of that compute region, we didn't copy anything. So it's much faster. We go through our different iterations. Now finally at the final iteration through, we copy it back at the end of the data region, and then deallocate the memory and continue. So now let's look at seismic. Seismic CPML. Well, first I should back up, give you a little history of why I chose this particular algorithm. I was invited to talk at back in September in San Antonio at the Society for Exploratory Geophysics Conference, or SEG conference. But instead of just coming up and saying, well, here's the directive and here's kind of how they work, I actually asked for, well, give me a representative code, something that's cutting edge, but also applicable to some of the problems that you as geophysicists would encounter. So I was given this code from the website down here at Geodynamics. And it's actually not just one code, it's a set of 10 Fortran 90 codes. I selected a single one of them. I tried to select the most complex one. It's a isotropic 3D finite elements wave propagation. So it's a fairly complex code, and my understanding is that it is a cutting-edge algorithm. It's kind of the state of the art for wave modeling through the Earth. In this case, it's modeling earthquake waves. It wasn't modeling the actual seismic waves that the geophysicists and oil and gas exploration do. But it was representative of an algorithm. So the one I worked with is also uses a MPI and OpenMP hybrid for its initial parallelization on the host, on the CPU side. So I am going to be using multiple GPUs for this. So let's look at some of the steps that I did when I was initially porting this, and steps that you would, as a user, use to port your code. So the first step, and this is actually the most important and often the most difficult step of all, this is the evaluation. Is my algorithm right for a GPU? Not all algorithms are right. This is a GPU is a throughput engine and needs lots and lots of parallelization. Without that, you're probably going to slow your code down. I kind of think of a GPU as an army of ants. Individually, each one of these thread processors are not that powerful. To get the speed up, you really need to utilize them all and have as much throughput as you possibly can. Let the CPU do what it does well, which is serial code, and let the GPU do what it does well, which is parallel code, specifically data parallel. So I looked at seismic and asked the question, is this right for a GPU? Well, the structure of the code is, it has a lot of setup code at the beginning. Then it goes through a time step loop. It's 2,500 iterations. Within that time step loop, there's 9 main inner parallel loops. Those inner parallel loops are highly parallel, perfect, ideal for the GPU. They're great. The problem, though, is it's an MPI code. And in my implementation, I actually took out the MPI or the OpenMP section for the GPU code. It wasn't necessary, so just focused on the MPI part. But even with MPI, you actually have to pass sections or the halo regions. That's kind of the blocks of your domain that are shared across the different MPI processes. Those have to be shared after each time step loop to make sure your data is coherent and consistent across all your nodes. So you have this extra copy, and there's 6 arrays in there whose halos have to be copied. So this coupled with the iteration loop, so it's still a good candidate. This I wouldn't call seismic like the ideal. This is not the poster child for GPU programming, but it's good. It's good enough and more realistic to what at least in this case, the scientists would encounter. So now that I've evaluated, determined where my parallelization is, if this is you may have to go back and look at your algorithms to make them more parallel. The next step is to actually start adding the directives. Because this is Fortran 90, we just define a region of code with bang $ACC region and bang $end region. So the bang in Fortran 90, if you're not aware, is a comment. So if the compiler doesn't recognize it, it will ignore it. So you can use other compilers. But here we're going to tell the compiler, okay, take this in this particular case, this is the 9th of the 9 parallel loops in there. And it's doing a reduction operation to get the total kinetic and potential energies of the waves. So next, when we compile this code, I'm going to add a flag. This is -TA. TA stands for Target Accelerator. Notice that I did say accelerator. This is a generic model. So currently we do only target NVIDIA GPUs, but the model is designed to be applicable to multiple accelerators, so different types of accelerators, not just NVIDIA. But for now, let's just target the NVIDIA GPUs, since at this point in time, NVIDIA has done a wonderful effort in terms of HPC computing and has made GPU computing more accessible. But that doesn't mean that other companies such as Intel or AMD won't be there in the future. So one thing you can do is you can be assured that when you do port your code to a GPU or an accelerator, it is generic, so it can be retargeted to other GPUs at a later time. Our second important flag here is called minfo, and that's basically you want the compiler to tell you what it's doing. This is the feedback. In this case, we're going to limit it just to the accelerator, the ACC or Excel here. It could tell you what it's doing on the CPU, whether it's vectorizing your code or what have you. But for now, let's just focus on the accelerator output. During your development process, this information is critical. We'll show you why here in a second. But everything you see here are things that you can affect. So the compiler is going to do its best job to tune your code for a GPU, but it has to be conservative. So in this case, it's going to enter this region. It can't evaluate on a whole program basis where your data movement is. It just doesn't have that visibility. Only you, the programmer, has that. So here it knows it needs these arrays, these VZ, VX, VY, so it's the sigma arrays, over on the GPU. So it automatically copies them over. Now, if you look at the dimensions here, that's actually not ideal. What's happening is it's only taking over the portions of the array that it absolutely needs. So it's doing the minimal amount. And the reason for that is because it won't know at compile time how much memory is available on your device. So therefore, it's being conservative. It's only going to copy the interiors. Now, this is going to be a performance problem because you actually want to copy in contiguous blocks of memory, and this is creating are forcing multiple blocks to be copied many, many, many times. So other information will give you this loop is parallel. What it's doing here is it's going through the code and doing classical compiler loop dependency analysis to determine whether or not your loop is actually parallelizable. Doesn't mean it's going to parallelize all the loops in there, but it's just doing that analysis. For the accelerator model, you want one, and preferably the outer loop, to be parallel. You have to have at least one parallel loop. You can't have things such as while loops or non-parallel loops inside that parallel loop. That's fine. Those will get actually generated into the kernel. But you do need one level, at least one level of parallelization. Here we have all three of the loops are parallelizable, so that's great. Because of that, the compiler has been able to create a schedule. That's what this line 108 ACC do parallel vector. Parallel corresponds in NVIDIA, on an NVIDIA GPU, it corresponds back to the block. So these are a two-dimensional block it's creating. And then a three-dimensional thread block, a 4 by 4 by 16 thread block within a two-dimensional block. Notice no widths on these parallel. That means that the number of blocks generated is a runtime variable. It'll be determined at runtime, as opposed to the thread blocks, which are a fixed size. You can fix size the parallel loops, and the compiler will take care of any fluff by putting in, having each kernel take care of multiple iterations of an array. We are a compiler, and what that means for GPU code is we can actually optimize your code. So other solutions do not have that advantage, and if you're using CUDA-C, how you optimize your code is you, the programmer, has to hand optimize it. Here, the compiler is able to do many things, classical optimizations, but it's giving us a little bit of feedback that it's using some registers here, and registers are highly important for fast data access because just like a CPU where you're using the register files there, it gives very, very fast access to each one of these threads. And data movement is our enemy here. Minimizing data movement is critical to performance. So as close as we can get this data to the processor, the better. And the compiler is going to try and optimize that as best as it can. It does give you some information back. So if some of you are out there are CUDA users, you can affect things like occupancy. Occupancy is the number of threads that are actually executing on, or will execute on the GPU as a percentage of the maximum that can execute. Here at 33% is actually pretty poor, but it's not the end-all metric. Just because we have a high occupancy does not mean it's going to go faster. And the reason why the different occupancies is because of how much resources you have on the device. It's finite. So here we have 43 registers, and that's lowering the number of threads that actually can be executed. But if you want more details on that, there's plenty of information about occupancy, or you can talk to me later about it. The compiler is also able to recognize reductions. In this case, it's recognized two sum reductions. If you've done sum reductions with CUDA, it's actually very difficult to get right, to get optimal. It's easy to get wrong, and I have written one which was very wrong and slow myself. But here, it's much easier. The compiler just recognizes that it does a highly optimized sum reduction kernels for you and takes care of that. So here, after my first step, very excited, it took me about 10 minutes, get these directives in. Yes, I managed to slow the code down by 3x. At least I only took the 10 minutes to do it. So why the slowdown? Well, you should all know by now, given that first C example, why the slowdown. Of course, it's data movement. We've got 9 parallel loops. Each time we enter those loops, we're copying data over and we're copying some of it back. We're going through a time step loop of 2,500 times. So for each of these 9 loops, we're copying data back and forth 2,500 times. And unnecessary. So instead, I added another data region. Here we've got our time step loop. So I'm pushing much of the data movement before this. In this case, we've got these half arrays and these AX, AY, and so forth arrays. Those are constant arrays. So we just need to copy them over once. And then these memory arrays are like A in our previous example where they're just scratch registers. So they're just holding information from time step to time step. So there's no need to copy them back and forth. You just leave them over in the GPU. I also did an additional optimization here. So I talked about it's not just about the amount of data, but how often you copy it. Well, this is an MPI code. So I have to pass those halos. Those halos are a particular Z dimension. And it's not necessarily contiguous memory. So therefore, if you want to copy that back to the host, the compiler has to do multiple copies through there. So this is the one part of the code, and I don't show it here. I can later if you'd like to see it. The one part of the code where I did modify the original source. And in there, I actually did a conditional compilation, so I used macros to define the region of the code that is only supposed to be used for the GPU. But there I added an extra little gather and scatter operation. So in other words, I gather from the 2D array, or excuse me, the 3D array to a single contiguous 2D array, and then copy the 2D array back. So instead of multiple small data copies out of this 3D array, I gather it up first and then copy it over in one block. And it is significantly faster to do that. So again, you may have to do slight variations of your code for the GPU, but we have ways that you can conditionally compile it through macros. So with these changes and optimizing the data movement, the time significantly dropped down to 194 seconds. And of that, only 4 seconds was in data movement. So I was able to use some profiling, in this case the CUDA profiler, to actually examine the exact amount of time that it took to copy data. It took a while for me to do this. It took about 3 hours to optimize it. And it gets a little difficult at times because now, especially in a data region, you have to keep track, well, am I acting on a host copy or the device copy? When in a data region, the compiler is not making any attempts to manage that. You have given up control from the compiler. You've taken control from the compiler and are starting to manage that yourself. So you may need to synchronize data. You do those through what's called an update clause. And you have to just remember, well, which variable I'm acting on. And part of this 180 seconds is a half an hour as I had to track down a bug because I missed one. I missed one of where I didn't put a host, where I was acting on a host, excuse me, an array. I didn't put that on the device. It was still acting on the host. So that took a little bit of time. I was getting wrong answers because of it. It's like, okay, I'm going to track that down. So it does get a little tricky, but the benefit is obvious when you can get that down. So you don't have to stop there. So most of the time, the compiler does find a good schedule for you. It's not guaranteed. Not guaranteed to be optimal. So it's always a good idea to go back and kind of look at your profiling, figure out, well, can I do better? Can I affect this? And I would say I usually give about 2 hours when I'm looking at code to see, well, can I do anything better? And most of the time I can't. Most of the time it's like, oh, I found a good enough schedule. I don't need to do anything. But in this case, I was able to find a bit better schedule. And the reason why is because I knew something the compiler didn't, because it's a runtime environment, is I knew that the K loop here was my smallest loop. It was actually fairly small compared to the others. So in that case, I wanted to push that into my thread block as opposed to it being, the original was a parallel vector 4, vector 16. So I just moved the parallel down to the inner I loop and was able to see a slight, not huge, but slight. So, but at this point, what we're working on is that last 10%, the last little bit of speed up. But in a little over 5 hours of work, I was able to get a little over 5x speed up. Well, that was on this little system. It's a small system, admittedly. It's only got 4 cores on it. It's got 2 GPUs. It's a nice little system. It's a modern Core i7 and fast system. Well, what happens when I move this over to a larger cluster? So in this case, it's a 16 node, 16 cores per node. It's a slightly older AMD processor, but the Tesla that I'm using on is a last generation Tesla as well, so I figured it was roughly equivalent. Here we're going to be comparing a much bigger data set for both. For the little bit smaller in quote, it's still quite large. It wasn't as great. It's about a little over 3x here, but when I moved it up to the 1024 size, I still saw that 5x speed up. Now, yeah, speed up is all relative. Speed up, it will vary on many different factors. I usually don't really even like to talk speed up per se, but it is the metric that most people use, so that's why I'm using it here. I like to think of it as I can get more work done. You know, if I'm used to my program taking an hour, and that's where I get my results, well, what can I do in that hour? If I'm doing weather modeling, that means I can get smaller and smaller grids that I'm doing. So I can get down to that 1 kilometer and get better and better details. If I'm doing quantum chemistry, I can do more of my molecules. If I'm doing, I saw one researcher that was working on, essentially they had this electron microscope type idea where you could get down and model the different elements of the molecules, and you'll be able to simulate that in finer and finer and finer details in the same amount of time. So it's not just about going faster, it's about doing more with the time that you have. So again, getting back to, you have to figure out whether the accelerator model is right for you. If you don't have a lot of parallelization in your code, you're not going to see that much speed up. So here, case, we have a 5-hour program that takes 5 hours, an hour of which is parallel. So even if we did that down to 0, Amdahl's law takes over here, and you don't see much. If you had 4 hours of that 5, and we're able to get it down to that half an hour, well, then you start to see good speed up. Now, I can turn this around saying, well, if this program took a month to run, well, and even if only 1/5 of that was parallelizable, well, you're still seeing a large increase in overall time. It's still an increase. So it's all relative. Speed up is relative. You have to put it in context of what you're doing and whether not just the accelerator model, but the GPU. The accelerator model goes hand in hand with the GPU or the accelerator that you're working with. What the accelerator does is it just gives you easier access to it and easier to program. Now, this is the ideal scenario. If you have these different elements to your program, the GPU is great for you. Now, if any one of these are off, it's still okay. You're just going to be losing some performance. So you want, the best way to think about it, what their accelerator model really is ideal for, is a highly nested, highly parallel loops with large counts. You want large counts. It doesn't matter if your loop only goes 24 times. Well, you're not going to see much speed up because the overhead of copying your data will outgain any computational speed up that you get on the GPU. So you do need to have large iteration counts. And at least some of the loops need to be fully parallel. If it's not parallel, it's not going to work on the GPU. You do need to have a rectangular loops. In other words, where the loop bounds on multiple loops are known upon entry into the compute region. So it can be launched on the GPU. The GPU is a rectangular. There are ways around that. If you are doing triangular arrays inside, you can work around it. You're just going to start losing a little bit of performance. And whenever possible, you want the data to be contiguous and contiguous across threads. So it's a little bit different than if you're used to MPI or OpenMP programming, where you want the contiguous, your threads to have blocks of code. Here you want each thread working on basically contiguous elements within your array. So I thought I'd mention here a program that we're doing here with PGI in conjunction with NVIDIA. It's a 2x in 4 weeks program. And the idea here is to get people to try the accelerator model, and it's kind of our bet, our guarantee that if you have an appropriate algorithm for a GPU, we can at least get 2x in 4 weeks. You can get a 2x speed up in 4 weeks. That's kind of the minimum in my mind. If you've got an appropriate algorithm, there's no reason why you couldn't do this. And as we saw, NVIDIA just put out a press release that showed in several in the first 2 weeks of this program, we had many success stories where people were getting 5x in one day, similar to mine, and they weren't experts like me in the model. So it is accessible. The guarantee portion of it is if you aren't able to get that 2x in 4 weeks, we're going to give you consultation to get you there. And you have free use of the compilers. Normally, our normal trial license is 15 days. For this program, if you sign up, we'll give you 30 days. It's actually in 2 15-day chunks. And the first 100 participants that respond to a weekly survey and kind of give us your feedback and tell us what you did will actually get a free license. That's compliments of NVIDIA. So it is an exciting program. Hopefully some of you can take advantage of that if you're not already PGI customers. So at this point, that's the end of my presentation. I'm more than happy to take questions. We can go over code or go into more details of anything I might have missed. So, fortunately, I I'm going to have to give control back to the moderator in terms of getting you guys to be able to speak, or please in the chat window.
Okay, I guess we can open this up to questions and answers. If anybody does have any questions or answers or questions for Matt, please feel free to enter them in the chat or the Q&A section of the WebEx. We will take those now if anybody does have them.
Other things to keep in mind is to go to our website, www.pgroup.com, just like this, where we have a wealth of information about the products. If you're interested in CUDA programming, CUDA Fortran programming, in addition to the accelerator model, we have a lot of information there. We do have a users forum if you have questions. I'm actually the moderator of the user forum, so many times you'll be talking to me at that point. Or feel free to email me directly. That's my email address right there if you have any additional questions.
Okay, thanks, Matt. And our first question that we just had come in is, what operating system can this operate on?
Linux, Windows, Mac. So we target all the major OSs.
Okay. If anybody else does have,
for some reason I'm not seeing the questions in the chat window. I'm sorry. So
yeah, that was the only one so far. So
okay.
If anybody does have any more questions, please don't be shy. Go ahead and enter them in the chat or the Q&A. But like Matt said, in the meantime, if you do have any additional questions, feel free to email him. His email address is up on the screen, as well as you can email TechXtend at salesassist@techextend.com. We'll also direct you to somebody who can get you the answer. Another question that came in is, does it work with MIMD or just SIMD?
I'm sorry,
MIMD or just SIMD?
Oh, SIMD, is that a D at the end? Okay.
Yeah.
Okay. Well, the SIMD, that's the architecture. So the thread blocks. If I can go back. Whoops. Yeah, it doesn't look like I can go back. That's fine. So the MIMD, multiple instruction, multiple data, are the streaming multiprocessors. They're able to work on different instructions. You can kind of think of how it's organized in these blocks, and each block is scheduled on a streaming multiprocessor. There can be multiple of those going on at the same time and working on different points within a kernel and being swapped in and out all the time as they're hiding the latency. But within the thread box, that's where the SIMD, the single instruction multi-data, it only works there. So, but that's a hardware detail that typically the programmer doesn't, at least with the accelerator model, you shouldn't really need to worry about to that level.
Okay, and another question, what's the relationship of PGI ACC to OpenMP?
Okay, so we are part of the OpenMP ARB board. That's the committee that actually does the OpenMP ABI standard. We are working with OpenMP to essentially standardize the PGI Accelerator model. And part of that effort, it's been a multi-year effort. One of the things that's come out of that is, since OpenMP is a little bit slower, it has more people involved, PGI, another company called CAPS, Cray Computing, and NVIDIA banded together and developed what's called OpenACC. And essentially what that is it's roughly 60–70% of it is the PGI Accelerator model, then revamped a little bit with Cray's input, and we kind of think of this as the predecessor to what's and it came out of the OpenMP committee, and most likely what's going to be brought back into OpenMP. So our end goal all along in the last 5 years since we first launched the Accelerator model is to get it to be an open standard, and preferably have that open standard part of OpenMP. The worst thing that can happen is that this is a proprietary model that you can only come to PGI with. We want other vendors to support it as well. We want it to be an open model targeting many different accelerators. And right now where we're at is the OpenACC. That just got announced at Supercomputing 2011 in Seattle. So it's a very new initiative. We will implement the OpenACC. We'll start adding the throughout 2012. We should be, most of it will be implemented in our first release here in January. Then some of the things that we need to add on throughout the year. So what I would say to you is, in the end, in a year's time, you're going to, if you adopt directives and pragmas, you're going to be using OpenACC. But in the short term, you can start with the PGI Accelerator model, because anything you do there will directly translate to OpenACC. And then you'll be able to utilize Craze, and hopefully in the future, some of the other major players will come on board as well.
Okay. Another question: are you able to get good speed-ups on FFT algorithms? How about time domain filtering in single dimension?
Right. So FFT is a little bit more complex. It will depend on exactly what you're doing. So I haven't done an FFT myself, and it'll depend on the density. So one of the things I haven't started yet, but I wanted to look at, well, is it possible to do sparse matrices? And probably the problem with sparse matrices is that it's really about how you gather up your data first, or if you have enough room on the GPU to put it all over there. So yes, it can work on FFTs. You may have to do some adjustments, however. It will depend on your particular algorithm, though. So.
Okay, and the last question we have so far is, can code written for Linux run in Windows?
No. I mean, there are emulators and what have you, but it's completely different object code running on. You can't just compile on Linux and then run it on a Windows machine. I'm thinking there's Wine and other emulator. Well, Wine is not an emulator, but the bottom line, for the most part, no. You would just have to recompile, though, and it typically, it's not always simple because there's different. The major problem is your interface between your host code and the OS, any system calls and whatnot, and those are not compatible between Linux and Windows. So it does need to be recompiled. Hopefully, though, you don't have a lot of those directly in your code, so it won't take a lot of effort. It's not a huge porting issue, especially if you're using Fortran. Then with Fortran, it's typically just you need to recompile. C, that's a little more complex because often people put things in there that are Linux-specific or Windows-specific, and those need to be ported around. So, but that's normal, C and Fortran programming. It's besides the accelerator model. Same issues would apply, though.
Okay, then thank you very much, Matt. And thank you, everybody, for attending today's webinar. If there are any further questions, please feel free to contact us at info@techextend.com via email or on the web at www.techextend.com, or call us at 800-441-1511, and we'll be happy to answer any questions. Thank you again, Matt, and thank you all for attending.
Well, thanks, everyone. Have a great day.